Hi, my name is Jeremy Sandifer, and I'm a Research and Extension Associate in the College of Agriculture, Community, and the Sciences. And today we're going to talk about the use of geospatial technology and helping us understand the relationship between climate and severe weather. So the agenda for the presentation is to briefly explore the relationship between climate and severe weather. We'll talk a little bit about the role extension has to play in helping the public think about these issues. We'll explore a few key African Americans in weather science and modeling in the early days of this science. We'll examine closely the differences between climate and weather, and we'll look at some key technology that helps us really visualize both the processes and how they're changing over time. And then we'll end with a few notes on how you can take action at home to be informed about this issue. So the role of extension in doing this kind of work is in promoting the study of human and environmental issues at the local and the global scale, and of course, everything in between. What we hope to do is to reach stakeholders with accurate and truthful information that they can use to help make decisions that are sustainable for either their operations at home or farm operations or land management or whatever kind of activities you may be into. And what we hope to do is enhance the public's environmental literacy so that they can develop critical thinking skills, especially as it comes to thinking about how we manage issues in the future. So extension, we really create a lot of opportunities for the public to be able to come and interact with where the science is taking place and just to get out into the real world and see how the community is interacting with science and business and agriculture. And we just try to create a lot of learning opportunities so students can get the experience and just see this stuff going, hopefully so that they can choose to pursue it as a career path, but if nothing else, just to get a feel for what's actually going on. So Earth Day itself is really within this same mission. So it's a day set aside to appreciate the Earth's environments and how important they are, and really how the issues and the decisions that we make about how we manage the land impacts how safe and healthy it is. So just as an example, just to show kind of how Earth Day came out, post World War II was a boom time in the United States. It was increasing industrialization going on. It was all kind of products being created and used out. And as we sprawled out from the cities into the surrounding countryside, we had to compete with the wildlife that was living out there at the time. And one particular troublesome chemical that was developed that was highly effective at combating these pests was DDT. And DDT worked wonderful for all kinds of pests that carried disease, but what they found was as it was applied over time, it would stay in the environment. And as one animal ate the next animal, it would accumulate. And then it would basically concentrate and poison all of the environment. And if you'll just look at the little example there in the bottom left corner, lots of birds that have to develop protective eggs for their young, these chemicals literally stole material from the eggs, and they simply couldn't survive. And thanks to Rachel Carson's book, Silent Spring, this was kind of the beginning of the environmental movement where the public was being informed about how their decisions impacted the environment. So this day is meant to celebrate that. And our role in it today is to explore how we're using geospatial technology to characterize these issues. So the beginnings of Earth Day, as I mentioned, was right on the tail of World War II and the beginning of the sprawling out of America. And since it was wartime and it involved the movement and lots of logistics, the weather was important. So if you're flying a plane, it's very important that you're aware of what the temperature and the moisture and the wind profiles are so that you can safely, move materials from point A to point B. So at this time, this is the very beginnings of what would later come to be known as the weather bureaus that we have now. This is the earliest outfit, weather clearance station, and this is in Tuskegee, Alabama. And these are some of the earliest pioneers in meteorology, both in terms of understanding the weather and then later being able to understand how it functioned, first of all, and then how it changed over time. So here, at the same time Earth Day is starting, this is at the same time where the first atmospheric general circulation models are being put together. Dr. Warren Washington of Oregon State University was among the many folks that worked on these very first models that showed how the Earth, as it received energy from the sun, moved moisture and temperature, around the globe. And those earliest models still today support the highest resolution models that we use today to understand our world. So what is the difference between climate and weather? Weather is the conditions of the atmosphere over a short period of time. When you go outside, or perhaps over the day, and we can measure this generally in terms of temperature, humidity, precipitation, wind, etc. And we measure this using a simple little climate station, as you see here in the diagram. Now, some of the stations can be much more complicated, larger, more expensive, but they don't have to be. And these stations are placed all over the world, and they measure these parameters, and this is the data that feeds those visualizations that I just showed you in the previous slide. Climate, on the other hand, is these atmospheric conditions, but over a long period of time, okay? And how these conditions change over time, over long periods of time, is what we've come to know as climate change. And we know climate change in terms of increasing temperatures, increasingly intense downpours of rainfall, rising sea levels, thawing permafrost, etc. So severe weather, and we'll take these one at a time. Severe weather, you know it when you see it. So while there may be proper classifications where after the fact they're able to go back through the record and categorize storms, severe weather is simply any setup of weather that is destructive to quality of life. So if it impacts your day in a negative way, we call that severe weather. Further, if it includes damage to real property or real disruption in the lives of those affected, like a massive flood, massive tornadoes, wildfires, hurricanes, and drought. So these affect all, basically all of the world, all of the U.S., and certainly all of these are threats here in Kentucky. Just this winter, we've been getting a lot of severe weather in the form of extreme rainfall. And this is just a satellite image taken from space, about 400 miles away. And you can see it late January, while it is very moist on the surface, 1 month later, you can see all these basins are filled with water. And this setup continued for weeks after. So to put that in context, severe weather in 2020, there were at least 22 episodes of severe weather that cost at least $1 billion to clean up. And that was just last year. How has that changed over time? The simple graph here, if you look on the x-axis from 1980 to 2020, on the y-axis you can see the number of events. So the boxes, as they're stacked up, the height of the box is equal to the number of events. And then the line, which may not be so clear to see here, is the amount spent on those storms, those billion-dollar storms. And the gist of it is that just this last year, we spent about $120 billion cleaning up after severe weather. In 2017 alone, the total was almost $425 billion. So the scale of the problem is very huge. And the chart also highlights, just as a note, that by far, severe storms take the lion's share of this. So this is thunderstorm, heavy precipitation, and generally fast flash flooding. Climate, on the other hand, like we said, is climate is the long-term record of the weather. And in terms of long-term change, a primary indicator is air temperature as it's measured at about 2 meters, which is roughly 6 feet. And while I have some facts here to show how temperatures have changed over time, NASA's provided this much more interesting set of images here that show how the temperature record has changed over time. So on the left-hand side there, again on the x-axis, you have from years 1880 all the way to the just a few years ago, about 2017 or so. And what they're showing is global temperature anomalies with respect to the 1950 to 1980 30-year climate mean, which is just a way of saying that over the course of 30 years, there's some mean temperature. So we set that to 0, and year by year, we can see how the mean temperature has changed relative to that artificial 0, right? And over that time span, temperatures have increased roughly 1 degree Fahrenheit, 1 degree Celsius, and that's for the globe. Now on the right-hand side, this is the same data, but it's being summarized by the month. So the idea here is to show you what the seasonal variation is of these increases over time. So some months the temperatures has increased over this time frame, more than 1 degree Celsius. And in terms of agriculture and land management, depending on when these key parameters of temperature and precipitation are changing, these could have drastic outcomes to how you're able to manage your land. The other primary indicator of climate change is precipitation. And precipitation overall is increasing. It's increasing basically all over the globe, but not by a lot. Not by a lot. 0.08 of an inch per decade over the century. But the big problem isn't so much the total rainfall, it's the patterns. It's the patterns that bring the rainfall. So especially since 1980, the prevalence of extreme precipitation events has gone up, way up. And all cities are really feeling the effects. These river cities like Louisville and Cincinnati, they've really been on top of this issue over the last little while because the infrastructure we have in place to manage drainage and river flooding and stream flooding and that kind of stuff was built at a time when the prevalence of these type of events wasn't widely recognized anyway. So in terms of climate change, more rain. And of course, I'd be remiss if I didn't at least mention space weather. So space weather is, certainly it's not as mainstream as the previous two types of weather and climate that we've been discussing, but it's very important, especially in terms of property and quality of life. So we all know that the sun provides most of the light energy that's available for the vegetation on Earth to do photosynthesis. Well, at the same time as this light leaves the surface of the sun, it's accompanied by what we call plasma. And this is just matter that's left over from the nuclear reaction that is the sun. Okay, and this is the solar wind, and we can measure this stuff, and it gives us an idea of how the activity on the sun is. Well, periodically, these much larger eruptions happen called coronal mass ejections. And these are magnetic storms, and when they dissipate, all the material that was involved in those ejections is thrust out. And NASA has a lot of missions that are studying this and looking at this because that material, when it's cast out through the solar system, just a few minutes after leaving the sun, it arrives on Earth. And when it crashes into our atmosphere, it does some beautiful things. So we know the aurora borealis, the northern and the southern lights, and that's the electrical energy being dissipated into the uppermost parts of the atmosphere. But some of the negative things is as it smashes through space, it can damage the satellites that are up there and the sensitive electronics that are taking all these measurements. During bigger storms, it can create voltage and power surges in our power lines, especially the long distance transmission lines. And over time, it can even corrode steel pipelines that are buried in the ground. And while it's still very much an open area of research, there's some indications that it certainly interacts and impacts the atmosphere. So to pull us back to our original question about the relationship between severe weather and climate, no single event or no single set of events even can be attributed to climate change per se, all right? And to really explore this exact issue, the American Meteorological Society every year will choose the 10, 12, 15 largest severe weather events, and they will look at all of the evidence that could be used to summarize how the frequency of these events have changed, or what parameters like temperature over time could have contributed to some of these individual storms. And the most recent version out now is 2019, and it covers like the hurricane that went through Puerto Rico. And again, while you can't attribute these single events to climate change, they certainly offer a lot of evidence that talks about how if the climate engine changes, then the likelihood of extreme weather is changing depending on where you are. So we can certainly say that vulnerability to increased severe weather is in large part based on the geography. We're going to turn now to Demetrio, and he's going to highlight for us another couple of examples of how we use this technology to monitor storms.
Good morning, everybody. My name is Dimitrios Zorakis. I welcome you to Earth Day 2021 at Kentucky State University. I am attached to the geospatial program at Kentucky State University in different capacities. I'm an adjunct at the University of Kentucky. Also, I do some contract work in the private sector and public sector. I have some 20-some years of experience with geospatial, GIS, and remote sensing. So today we are trying to show the influence of climate and weather in on natural resources, and give you some tools to discover data pertaining to those very important areas. So we have a set of slides today, and we have a few demos that we're going to show you. And my first slide here shows how weather can be monitored from space. And this has been going on for many decades now, but it's kind of a given that people would open just the newspaper, the back part of the page of the newspaper, or open up their weather feed or service on their phone and look at the map. Okay, so everything is about maps, really, in a way. Everything happens somewhere, and spatial. But all these data that are coming in are from craft that are orbiting the Earth and observing, taking measurements through different means. We're going to talk about that in a bit. So right now we have the National Oceanic and Atmospheric Administration has weather satellites that pretty much rain on us billions of observations, petabytes of data. Every day, every week, every month, I mean, data are piling up, and we can make contrast studies, change detection, how the weather is changing, how the climate is changing, and that's what we're going to show some of that today. So all the weather forecasts and all the warnings are based on models that they have that get data that are fed from the sensors that are on board the satellite. So one of the examples I chose for today is the NOAA 20, which is a joint polar satellite system. Okay, so we have a acronym soup of letters today, just agency letters and all kinds of things. But we try to spell out every single one of them, okay? So the National Weather Service has this satellite as the source of information. The sensors aboard the spacecraft are instruments that measure something. Usually is either on the some type of electromagnetic radiation that comes from the Earth. And as you know, we don't have enough time to go into a typical remote sensing class, but we're going to talk about a little bit about visible data, some sort of radio, microwave sounder, which is like a radar, then some infrared sounder, and then some clouds and Earth radiant energy system. They're all listed here, all these sensors. They measure atmospheric, terrestrial, and oceanic conditions via different parts of the spectrum, okay? And then the models designed by physicists combine all this information and create data like ocean temperature, atmospheric temperature, atmospheric humidity or vapor content. So here you have, for example, on this this map shows the temperature of the atmosphere based on a certain channel. Like sensors have different channels. Like your radio has, your cell phone has channels. The radio has channels. So in the end, the product is a map. It's a map of, say, vapor content of the atmosphere, temperature, or oceanic temperature, surface of the ocean. So right now we have the sea and land surface temperatures map, the vegetation map, the clouds, water, vapor, and rainfall, snow and ice cover. So all these products have been increasing in diversity over the years, and they are available for the public to download as either the raw data or the model data that they come up with. Some of them are very, very visible, like fire location and smoke plumes, volcanic ash and gas. I'm sure you have seen some of these maps, some of these images from the space station. More subtle is atmospheric temperature, like this map shows right here, right? So is the Earth getting warmer? Well, that's the only way to answer it, is to just measure it somehow, right? Well, this is how we measure it from space. So again, the NOAA 20 shows a dramatic change in temperatures over North America. And these are the maps right here, right? We would not have been able to make this map without the satellites that NOAA has, the NOAA 20 particularly. So the red, you know, that's the symbology at the bottom, and of course, you know, the degrees Kelvin, of course, and the deviations from normal. Another thing that NOAA has is the geostationary satellites. For example, every time there's a hurricane, we wonder how they know when the hurricane is going to make landfall and where it's originating from and what the track is of the hurricane. So we want to go in there to this page and that's on the Facebook. It's a Facebook page that has a video where it shows you how a geostationary satellite works. It's parked in orbit, and it orbits with the Earth. So we're going to go to this page now. So here we have the Earth, and we have the sun illuminating the Earth as it turns. So remember that the satellite and the Earth are turning together. That's why this effect is visible. Now, if you pay attention, you'll see that the weather systems are moving. It's because I'm fixed in a fixed position with respect to the Earth, so I can see this movement. That's relative to us. So you see the, let's see. You see this cloud systems moving and changing location right there. Always remember that there's military and civilian missions, and the satellites will carry sensors that are intended for both purposes. So we have here the military weather satellite as well. So there's different agencies that measure not only Earth weather and climate, but also space weather, right? We will not go into that, but it's on the news already about solar flares and solar storms. So weather, when we say weather and climate, it has broader implications than what we know. And all these satellites, all these missions have satellites, which are the vehicles, and the vehicles, the platforms, have sensors, instruments. So I gave you some examples of that. One of the clear results of weather is weather events. And we are going to try to show you a little bit more of how remotely sensed data from the air, not only from space, but from the air inside the atmosphere, right? From a plane, and say an aerial, a mapping camera mounted on an airplane can see some of the disturbances that are created by weather. In this particular case, we are going to go to a tornado tracking web mapping application, the tool. So this tornado tracking tool that is that's shown on the screen is a map, right? Mapping application that allows me to choose the different tornado intensities and the different time periods. So some people want to see all the tornadoes that ever happened in Kentucky, so we are going to just change this to this time period, and they do happen, and they're very frequent over the period of time. But we're going to just focus today on the March 2nd, 2012 events, my birthday. I remember driving back from Milwaukee from a conference, and the weather was really violent and pushing east. And these are the tornado tracks reported for that day. So we're gonna focus on the eastern part of the state, the West Liberty tornado and the Magoffin County tornadoes. These are the tracks that were reported by people. Okay. So one way to monitor and inspect and discover the effects of weather or climate on natural systems is to compare different aerial photography or imagery from different dates. So in this particular case, I chose the 2010 to 2012 comparison. The tornadoes happened in 2012. So these images here from the National Aerial Imagery Program that the USDA, the U.S. Department of Agriculture has, they fly the state every other year. And these are at 4-band, meaning that they are multispectral data. Now, we don't have too much time to explain what that means, but imagine that you have red, green, and blue colors or bands, and then a near-infrared band attached. We're not going to go into near-infrared false-color photography here, but we are going to use the true color, real, natural color imagery. In this particular case, you have these two. So we're going to focus on the eastern part of the state, like we said before. Those tornadoes were devastating for a community in West Liberty and others. So the application, the web mapping application we're going to use today is the ArcGIS Online application. Okay, so it's an Esri product, very common in the market, very common everywhere. I mean, all the story maps you make, are Esri technology, and this is the one that anybody can make a map if you know where to find the services. So here I have a map, and I have a table of contents that shows me the layers I'm gonna use. I want to use the 2010 and 2012 imagery for the whole state, like I said, true color, and I can go in here and turn different images on, and we have. I'm gonna zoom out a little bit, and we have the 2012 versus 2010 comparison. So if you zoom out a little further out, not that further out, it's going to refresh the image in a second. There it is. So this is a tornado track right here. So if you were to just look at the original data from 2 years before that, those are trees that are missing. This is forest that's missing along that line. And there's other tracks. There's one in Magoffin County, further south, if I can do this. You see these are all mined out areas, but you see one here, one track right there. So there were other tornado tracks that were not reported because there weren't people seeing it. So maybe these events are more common than we think. And this is a way to really quantify the devastation. One of the important things that one has to remember is that many of the data are in the cloud. They are published for everybody to consume as services. We find these in this type of thing. It's an ArcGIS REST Services Directory, courtesy of the Commonwealth Office of Technology, Division of Geographic Information Systems. And one could find imagery, many types of imagery. The ones I'm using are these two right here. So when I go to this page, it will show me the metadata, which is the data about the data. So it tells me what was acquired, when what is acquired, with what camera, what plane, et cetera, et cetera, et cetera. So it's very important to know what the provenance of the data is, okay, where the data come from, so we can assert its authoritativeness, the authoritative data. Same with the satellite data. The satellite data have been vetted. The sensors were designed to measure certain things, and then they were tested on the Earth, and then they were put in space, okay? So, and they check their accuracy all the time. So if the sensor goes bad, like your phone goes bad or your camera goes bad, they know how to modify the data so the data still are good. Another best-kept secret in Kentucky, the Kentucky Mesonet. The Kentucky Mesonet is a network of weather stations that eventually can tell us something about the climate change, right, on the ground. So it's a high-density mesoscale network of automated environmental monitoring stations, meaning that they're there while we sleep, acquiring data. Some of them have cameras. I don't know whether they're pointing at the sky, but remember that there's some cameras that catch meteors and bollards at night. Okay, so it's like you can catch all kinds of phenomena, weather phenomena. So this provides opportunities for Western Kentucky University student employees and interns to work side by side with professional staff. So this one is here shown is the one in Todd County. We're going to show a map with the locations in a minute. So this is a published paper. It's a scientific paper that talks about the Mesonet, and it gives a little more detail. So weather and climate observing network with redundant sensors, meaning we have many, many different sensors that measure sometimes the same thing. 71 locations across Kentucky. They measure temperature, precipitation, solar radiation, relative humidity, barometric pressure, and wind speed and direction every 5 minutes. With soil moisture and soil temperature measured every 30 minutes. So in addition, it operates a camera at selected locations. All observations are transmitted via cellular modem every 5 minutes and become available to the general public, and I want to show you that in a minute, through the World Wide Web within seconds after arrival. So these are examples. Okay, so these stations are located in kind of representative sites, usually farms, open spaces or pastures that they're fenced off so that no one can disturb them or vandalize them, but there have been cases. So these are the examples: Owen County, Carroll County, Mason, and Campbell County. So the surfaces are, pretty consistent. They tried not to have like near trees, forests, or the edge of the forest, or in on a weather corridor where wind speed is crazy. Just so there's a method there. Again, I'm not a meteorologist. Disclaimer. So weather on the ground. What do they measure? They have all this smorgasbord of atmospheric conditions or parameters, and they have a sensor. And the sensor here is a Thermometrics platinum resistance thermometer that measures what? There's the official air temperature measurement. That's an average of 3 PRT sensors located in a fan aspirated radiation shield. So these are standardized observations. These are calibrated, okay? So we can compare them. It's not like, stick my finger out and see how cold it is or where the wind is blowing from, all that. So. And dramatic example of a time series for 2 parameters. One of them is temperature and solar radiation in Christian County during the eclipse, the 2017 eclipse. So they turned off the light, so the temperature dropped, right? The Mesonet webpage, the homepage, allows you to interact with data and download data and request data, okay, to your heart's content. There's tons of data, right? So one thing we're going to show here is the way that one can select the data by county, by date, by type of atmospheric variable. So here we have the for Warren County, which is the way the default is Warren County, their own station near the university, at the university probably, where they have they show you a graph with the temperature, air temperature, dew point, relative humidity. So 3 variables. These data points are gathered every 5 minutes, and you can see how there's a trend. Today is the first sunny day in a while. Temperature is rising, humidity is dropping, and so this is one way of looking at the data. We can explore by county, and then we go down to Franklin County here. They are not sorted alphabetically because there are different epochs on the Mesonet where they have been adding stations, and not all stations are compared. So I'm going to go to the monthly summaries here. And I can see the counties: Franklin County, Frankfurt, F7S is the relative location, lat longs for them, the elevation, time, and here's your temperature for different dates. And so you can explore different years and different months. February was a really brutal month. We had single digits here and all that. So anyway, for those of you who do time series and analysis on climate and meteorology, this is a wealth of information. Another way I can interact is with the graphs, which you saw a minute ago. This is the graph for Warren, but I can choose Franklin. Franklin County, this is outside this location, and we have the temperature going up towards the 70s, and the humidity going down, and dew point kind of staying the same. We have quite an unlimited supply of humidity from the previous rain and all that. So another way of interacting is with a map. One of the variables that they measure is wind speed, and you can see how how they attach a vector, a direction to each location. So we know that higher wind speeds, this is one of those days when you could see the wind increasing, some sort of front or changes in the conditions. So you have higher wind speeds in different parts of the state, and half of the state or 40% of the state is quiet, single-digit wind speed, miles per hour, whatever, miles per hour. So another way the way to consume this data, right, is either you go and download a table, and you make your own map, or you can have an RSS feed, Real Simple Syndication, that's what it stands for, that allows you to bring in the data every 5 minutes into your web application or any application that you have. For example, you can create an app for a cell phone that consumes that feed and puts the data on a map. And this is what we're going to see next. So we're on the ground from Kentucky Mesonet, but now we have the folks at state government, Commonwealth of Technology, Division of Geographic Information, that created a Kentucky weather map application. So we're going to go there. So Kentucky weather mapping, right, with a feed directly from different services from NOAA and National Weather Service and the Kentucky Mesonet. So if we were to zoom in and click on Frankfurt, we see the conditions right now. Every 5 minutes, this is refreshed. Remember that. So we have here on this scroll bar on the side, we have the timestamp, March 16th, 3:10 p.m. We have the location, the lat long to the 6 digits, right? Elevation, wind speed, solar radiation, wind direction, relative humidity, air temperature, etc. And if you click on the more information, it would take you to the Mesonet. So this is the result of not only weather from space, because all these radar data are on the ground, but the humidity data also are from space, and they can measure also wind direction. And from the weather on the ground from the Mesonet. So we want to thank you for the time, and we hope that you can explore. All these slides have live links, and they're current. So if you have any questions, you can contact me or Dr. Budi Jawali at the Geospatial Program at Kentucky State University. And happy Earth Day 2021, everybody.
So now that we've explored the science behind severe weather and climate change, what can you do at home? How can you participate in helping push environmental literacy? Well, you can start by knowing your risk. Where you are, where you live, where you work. Knowing the risk is half the battle. And once you know your risk, you can start to take mitigation and protection efforts. You can install safety features at home or on the farm, try to mitigate against rough rain or high temperatures, freezing temperatures, whatever. The key thing is to monitor the patterns and the setups and to know the type of weather that your area has experienced and what it's likely to experience in the near future. We're going to provide a handout, a little exercise that's going to walk you through using some of the applications that are available, some available from the government agencies that are in charge of this, and some that we've built in-house at Kentucky State. So we'll be providing the exercise, and we'll go to some of the archives for the historical data. You'll draw data to understand how storms and the types of storms, how they've changed over time, and how the frequency and the magnitude of them have changed over time. And then we'll point you to other applications that'll show what the projected risk is moving in the future. You'll complete these exercises, and hopefully you'll be inspired to do additional projects, and we stand ready to help you find your way through that. And lastly, everything that we do is very expensive, requires a lot of money, both for the staff and the students involved and the equipment that we need. And all the work here that we've presented was funded, at least in part, by National Science Foundation, reviving and strengthening STEM instructional research programs, increased minority participation at Kentucky State, and preparing the pipeline of next generation STEM professionals. All right, so I hope that's been informative. As a reminder, my name is Jeremy Sandifer. You can reach me at jeremy.sandifer@kysu. If we can help you in any way to explore some of the concepts and the information that we shared, or to think about how you could start new projects, either at home or in the classroom,